Hello and welcome back to the second video of my 5-part series on how to do every single question on the 2022 Practice Exam 3 MCQ for AP Physics 1. So we're starting off with question number 11. Here it shows us a table, two different surfaces, a block and another block like this, except it's more circular. And it tells us that once it gets to surface B, it speeds up. So we can tell then at kinetic friction, the coefficient of kinetic friction at A is greater than the coefficient of kinetic friction at B, since it speeds up. And since the coefficient is greater, that means that this eliminates two answers where it says mu of B is greater than mu of A. We can also just reason that since it speeds up, the force is going to increase because the mass doesn't change. And since velocity increases, then we know acceleration is greater. So we can find that F of B is just greater than F of A. So our answer is going to be mu of A is greater than mu of B, and that's force increases. Question number 12 asks us for the force, or for the acceleration, magnitude of acceleration of the robot after it pushes a doll on a frictionless surface with force 0.3, and it also gives us that the mass of the doll is equal to 0.2, mass of the robot is equal to 0.3. So since it's frictionless surface, the amount of force that the robot pushes on the doll pushes on the robot, just to do Newton's third law. So we just substitute all the things into the equation. You don't need the mass of the doll here, so force is equal to mass times acceleration. 0.3 is equal to 0.3 times acceleration. Acceleration is equal to 1. That's the wrong tool again. Right. Now we're going to go to question 13. Question 13 is probably the hardest question on here, in my opinion, or one of them. So it gives us a sphere, 2m, and a box of m, and this rotates here, this shouldn't be on there, and it hits the sphere in an elastic collision. So kinetic energy is conserved as well as momentum is conserved. So first thing we need to do is find the velocity during the collision. And since momentum is conserved, we can find that the collision is equal to 3m v of x, which is equal to m v of 0. If we just cancel out these terms and divide by 3, we get v of x is equal to v of 0 divided by 3. This eliminates c and d since it's not v of 0, and so we're left with v of a and v of b. Now what we want to find is momentum of the sphere after the collision. So we know momentum is going to be 2m, and it gives us in the other part of the answers that the speed, the velocity is roughly 2v divided by 3. So we're going to get 4m divided by 3 v of 0. And well, we need the total momentum to be equal to mv of 0. So mv0 minus 4/3 is going to be equal to our momentum of the box right here after the collision, which we're going to do is mvx again, but a different mvx. So I'll just add like a little thing right here. Well, this is just 3/3 minus 4/3, so we get negative vx v0 divided by 3. So we know it goes to the left. So our answer is going to be A. That one's not really difficult, however, it's just a lot of steps. Moving on to number 14. Number 14 asks for the ratio of kinetic energy of blocks after a collision. So it gives us that there's a block of mass m sliding along a surface with kinetic energy k of I. So we know the kinetic energy at the beginning is equal to 1/2 mv squared, which is equal to k I. So then this block collides with another block of mass 3m. And then the two blocks stick together and slide together with total kinetic energy of k of f. So it asks us to find what the ratio of k of f to k of I is. So first thing we have to do is we have to find the momentum of the two-block system after the collision. Momentum is always conserved no matter what. So the momentum at the beginning is equal to mv0. The momentum afterwards is equal to mvx times 4. So we know that v of x is equal to v of 0 divided by 4. That's just because we make these two equal to each other, and then we divide by m, and we divide by 4. V of 0 equal to v of 0 divided by v of x is equal to v of 0 divided by 4. And we just substitute this into the next equation. K E is equal to 1/2. Our mass is 4, and then v of 0 divided by 4 squared. This could be 2, and this is going to be v squared divided by 16, which gives us 1 over 18. V of 0 squared, that should be an 8, not an 18. 1 of 8 divided by v of 0 squared, which is equal to k of f. K of f, k of I, takes 4 k of f's to get 1 ki, so we know our ratio is 1 to 4. So the answer here is D. Moving on to 15. 15 asks us for the acceleration of a meteor due to gravitational forces exerted by a planet. So here, it just wants us to find acceleration. Acceleration of gravity is just going to be equal to g here. This is not the g on Earth, this is g in general. So we know that g is just going to be equal to the gravitational constant times the mass of Earth, which is 5.97 times 10 to the 24th divided by 0.9 times 6,000 squared. Plug this into our calculator. It's going to give us roughly 10. And gravity always points towards the center. Therefore, the answer is going to be C. 10 meters per second squared towards the center of the planet. Moving on to number 16. Number 16 deals with the same exact thing, but it's asking us for the torque on a meteor with respect to the planet Earth, to the planet here. So if the meteor is here and it's in orbit around, it's orbiting parallel to planet. So there cannot be any torque. Torque requires it to be perpendicular or orthogonal or normal, or however you want to say it. So our answer is D, no, because the planet exerts no torque since it is parallel. Moving on to question number 17. Question number 17 asks us about a satellite with two thrusters on it. This thruster here, the thruster here. This one's going this way, this one's going this way. They're both moving counterclockwise. So it asks us, how does the mechanical energy of the satellite Earth system change, and how does the shape of the orbit change? This is just going to cause this angular momentum to go faster. That's all. It's not going to cause the shape of the orbit to change at all. So shape of this orbit will always be an ellipse, and it won't change at all. However, the mechanical energy of our Earth satellite system will change. This is because we can consider the thrusters as an external force, and that it's not part of the system, that we couldn't factor it in. So these going off, there was no potential energy of that due to either gravity, and no potential energy due to spring constant. And since the force is higher, it just makes it go faster, which means our velocity gets higher. So ke 1/2 mv squared. We just know that this is going to get higher. Therefore, our mechanical energy changes, but our orbit does not. And our answer is going to be C. Moving on to question number 18. Question number 18 asks us about the horizontal and vertical components of velocity. Boom, boom, boom. Gives us, this is the angle theta. We have a box here, m, and it gives us our coordinate is like this, x plus and y positive. And so it asks us to find if the velocity of the horizontal and vertical components. Ooh, College Board's not working. Who would have guessed? So we know that the box is going to slide down with velocity this way. But this isn't on any axes, so we have to get it here, here, back. This angle is going to be equal to somewhere around theta. So our horizontal component, we know, is going to increase because it's being pulled down with the force of gravity, which is equal to m times g. We also know that our y is going to increase because of m times g. So our answer is D. Horizontal and vertical components increase. Wow, College Board, please work. Question number 19 now. Question number 19 asks us for the change in kinetic energy of a box on a vertical spring. So it gives us this diagram first. I'm not very good at drawing springs, so bear with me. We have L0, that gives us a box. This is L equilibrium. And that gives us another one. Box here. Bah. L compressed. So it asks us to find where the kinetic energy will be the greatest. Well, we can factor L of comp and L of 0, since those will have high potential energy, especially L of comp. Next, we just need to do it down from D and B. Well, for springs, the point where it's going to have the biggest kinetic energy is always going to be where the equilibrium point is. This is where, when it goes up, it's going to go up at the fastest pace, the velocity is going to be highest here, and then the velocity is going to end up going down a little bit, but velocity will be at its max in the equilibrium point. Therefore, our answer is B. Moving on to number 20. Number 20 asks us to find the change in kinetic energy for different forces. So, all we have to do here is find our velocity. And this really easy way to do this is we just use the final momentum. Since we know P is equal to mv, and we know the mass of both carts given, so P of 1 is equal to 10, P of 2 is also equal to 10. Well, P of 1, the cart's mass is just 1, so we can just divide that by 1. We get our mass is equal to 10. P of 2, mass of the cart is 2, velocity is equal to 10 like that. mass is equal to 2, so we get velocity is equal to 5. Kinetic energy, final kinetic energy of cart 1. It also just gives us that it's 50. And then, so the second one, we just need to find this, put into the equation. 1/2, 2 of m, 5 squared, cancels out, and 25. 25 is less, that's not the right side, it's less than 50. So the answer is the 1 kilogram cart has a greater kinetic energy.